Hello, ladies and gentlemen. My name is Paula Cunha, and I am very pleased to be here today to talk about the research made by Jessica Sorango, Dr. Ana Gabriela Aro, Dr. Pablo Caiza, and myself. This work has been executed in the Earth Sciences and Construction Department at Universidad de las Fuerzas Armadas ESPE as part of the activities of the Structures and Construction Research Group, GIEC. Having said this, I do hope you all enjoyed this presentation. Welcome everyone. I would like to start by recalling the importance of structural walls into a properly seismic behavior of reinforced concrete structures. As you know, because of the length to thickness ratio, these structural elements provide substantial rigidity to high-rise buildings and overall structures. And precisely because of this, they usually compound the main lateral resistance system. Regardless of the shape of the wall in seismic regions, most of them will have concentrated reinforcement in their ends. This concentrated region is called as the boundary elements, which has a lot of importance in this study as we will see later. The lateral instability produced by the occurrence of out-of-plane buckling was first evidenced by Osterle in 1976, who carried out experimental tests on rectangular barbell and flange-shaped walls, where one of the rectangular ones, more specifically the R2 specimen, buckled. So we may say that was the first record on experimental program. Nonetheless, bibliography usually considers the research made by Gutzer in 1985 as the precursor of this topic. This is because the aforementioned author implemented a larger number of tested specimens either in structural walls and reinforced concrete prisms, which represents the boundary elements. He tested the latter elements after identifying that extreme regions of the wall are the most affected ones when subjected to reverse cycle loads. In the figure in the right, we can see a scheme of a buckled wall. It is important to mention that from that point, the approach of testing only the boundary elements was the preferred one because of several reasons, such as the economic and space savings as well as the accuracy of its extrapolations. Besides, it is also necessary to expose what exactly is the out-of-plane buckling reported in concrete walls. And first of all, we need to know that it's a mode of failure which concerns only seismic regions since it needs the occurrence of a lateral in-plane loading. So, upon the characteristic load reversals from a seismic event, the end regions experience tension compression cycles, as shown in the figure. And during the tension cycle, wide cracks develop, and within these cracks, the longitudinal reinforcement is subjected to large tensile strains. Eventually, the cracks can be observed clearly with the naked eye, as it was evidenced in one of the specimens tested by Almeida in 2017. During the compression cycle, the tensile stresses in the rebars reduces to zero, but the cracks could remain large. And this is a critical time since it was noticed that longitudinal bars located on the boundary region served as the only source of stability in the compression zone due to wide cracks that were still open from a previous inelastic tensile demand. Hence, after the subsequent reversals, there are two possible scenarios. The first one will occur if the out-of-plane deformation is relatively small, so the cracks are able to close and therefore permits the wall to return to its original straight configuration, which would be the case C. And the second one will take place if significant out-of-plane deformations occur resulting in a P delta moment that exceeds the moment capacity of the section, resulting in the loss of load carrying capacity and the consequent failure, which could be the case D. In these photos, we can see evidence from what I just said, but in real specimens. In the first place, we have stable cycles where the wall is able to come back to the initial stage after a complete cycle. But then, upon more, a brittle failure occurs. The photos correspond to one of the prisms tested by Aaron in 2017, and in the lab you also can see quite a similar performance in a T-shaped wall with only one layer of reinforcement. Great. So, taking into account the patterns of the failure, Pauli and Priddle in 1993 proposed a model that relates the tensile strength due to in-plane loadings to the out-plane deformations and relies on a stability criterion, which is a function of the mechanical properties and the longitudinal reinforcement. After some years, more specifically in 1999, Chai and Layer improved this first equation by considering the impact of cycle loading on the strain of tensile steel and a more representative curvature distribution. And for this new equation, the stability criterion is the same as the one proposed by Pauli and Priddle in 1993. We might say then that after the development of these two phenomenological models, the study of this failure was kind of forgotten since it had never been evidenced in real structures. However, that situation changed in the following years when an earthquake of 8.8 magnitude took place in Chile in 2010, affecting more than 300,000 structures, and where a repetitive motor failure was reported in various edifications. Then in 2011, New Zealand was affected by a 7.2 magnitude earthquake where similar observations were made. The failure evidence was associated with an elastic lateral instability, which called the attention of investigators worldwide and motivated several experimental programs, as well as the proposals of new prediction models. And as part of these new models, we have the model proposed by Arrow in 2019, which constitute the main rationale of the model proposed herein. As we have seen, there are plenty of phenomenological models and about 2 or 3 more numerical ones, but none of them have considered the concrete cover as an important parameter during their development. And given that concrete has been identified as a critical parameter for the onset of out-of-plane buckling instability, the approach presented in this paper includes the effect of the aforementioned parameter. For this purpose, a fiber-based parametric study was established for 120 column-type specimens that simulate boundary elements of special walls with different head-to-thickness ratios, and longitudinal steel ratios were combined with 2 cover thicknesses in order to propose a modification to the equation previously developed by Aaron. Well, as I mentioned before, the model proposed by Arrow is the benchmark of this new proposal, so it is worth to know that it considers 3 hysteretic components for the longitudinal reinforcement. First of all, we have epsilon sub A, which is the axial strain at first crack closure. We have epsilon sub E, which is the elastic strain recovery that depends on the elastic properties of the concrete and the transfer connection between the steel and concrete. Finally, we have epsilon sub R, which is the reloading strain associated with the compression yielding in both the reinforcement layers subjected to compression. Commonly, both epsilon sub E and epsilon sub R are expressed as a function of the longitudinal reinforcement yielding a strain, epsilon sub Y, as shown in the equation. So, for the parametric study, 6 geometry types models were considered, as we can see in the table, for a clear height of 3 meters and a length of the boundary elements as twice the thickness. The transfer reinforcement was calculated according to ACI 31814 dispositions, and the amount of reinforcement varies between 1 and 3%, passing by 1.5, 2, and 2.5%. The mechanical properties of the materials are shown in the table, both for the steel reinforcement and the 2 types of concrete used. This is the 28 and 35 megapascals. The program used was a finite element method 1 called Sysmostruct, where a nonlinear static time history analysis was conducted, and 6 finite elements represented the boundary element with fixed supports at both ends. We took into account 200 fibers and 6 integration sections. Regarding the loading protocol, the specimens were subjected to axial cycle loads, and the tensile targets were established as a 3-cycle loading, depending on the yielding strengths, fractions, until reaching the maximum tensile strengths that leads to the outer plane buckling stability. The compression loads were determined based on the maximum compression capacity of each boundary element. We also have the failure criteria, which is assumed that happens when concrete crushing is exhibited in the area where the highest strain developed. Thus, a concrete strain equal to minus 0.004 was used as the failure criterion to stop the analysis. Since this research corresponds to the case of a constant strain gradient, the greatest out-of-plane deformations occurs at the half of the clear height, and that is assumed at the center of the section, which correspond to the green bars in the figure. As usual, some data also had to be removed, so boundary elements with an aspect ratio of h/30 were discarded due to convergence problems associated with the insufficient cross-section to carry the load cycles before experiencing out-of-plane buckling stability. Other discarded specimens were those with an h/5 aspect ratio and some with h/10, since they exhibited concrete crushing because of robust cross-sections. In other words, the extreme cases oppose a problem because they are either too strong or too slender. So, with the results, some trend functions were elaborated. In this figure, we can see functions for the amount of reinforcement versus the maximum tensile strengths. Once the results from the boundary elements that presented a different failure mode were removed, of course. The predictions for each aspect ratio, calculated with the equation proposed by Arrow, were also included, and they suggest an adjustment despite their similarity. In order to develop the new equation, the terms epsilon sub e and epsilon sub r were associated and linked with the yielding strengths. The concrete cover COV is subtracted from the thickness since it decreases the core contribution as it is shown in the equation. The figure shows the influence of the amount of reinforcement in the cover on the normalized values of epsilon sub e and epsilon sub r. And the coefficients that best fit the result from sigma struct are obtained from interpolation and extrapolation of the confidence limits given as a result of the equation we are gonna see now. Yeah, and if we remember the three components of the maximum tensile strengths, now we need to join these two components, I mean epsilon sub e and epsilon sub r, with the epsilon sub a, which is the final proposed equation. Also, if we compare with the previous equation, we can see that it's very similar in its structure, but achieve different and more precise results. Here we can see the accuracy of the new proposal. The red line indicates the results from sigma structs. The blue line makes reference to the previous model of Arrow, and the green line is the new proposal. And finally, some real experimental information was taken into account, giving us results that even when the two models are very similar, the new proposal better approximate and predicts the maximum tensile strengths. And as a conclusions, we have seen that the higher the cover thickness, the less the tensile strengths. The new proposal also better predicts the onset of out-of-plane buckling instability when compared with its predecessor and predecessors in general. We have also seen that slender boundary elements present out-of-plane buckling sooner than thicker ones, and that the high-heel longitudinal shear ratios exhibit a reduced out-of-plane buckling stability capacity. So that would be my presentation. I hope you really liked it, and here you have the contact information. If you have any question, please do not hesitate to contact us.